Good afternoon. Thank you very much to Libby and Alejandro for inviting me to be part of this session. It's really an honor to me. Thank you, Jim. I will speak about a project that we developed in our university as part of a PhD work that one of my students is working on. It is related with a byproduct from the toilet industry, that is vitrified clay, and we use it to produce ultra-high performance concrete. First, I want to share with you what was Ramon for us. I met Ramon in 1993 in Vancouver in the ACI convention, and it was also a mentor for me and for many of the professors who work with us in the Universidad Autonoma de Nuevo León. Ramon was always very kind to share his knowledge with us and with our students. And we think that Ramon, it was like a big brother for us, the professors in our school, and as a grandfather for our students. I don't know the translation of jodido in English. I look for the translation, but I find a very bad word. So but Ramon always, when you meet him, he always says, how are you, Ramon? Jodido pero contento. That's what he always says. So I cannot translate jodido, but I can translate contento, happy. He was always happy. Well, okay. So that was Ramon always wanting to share. So when he go to our university, our auditoriums, when he give a presentation were always full, because he always, in the presentations, he always say a joke. Okay, he always making jokes, so that was very attractive for students. Okay, it's a very special way that Ramon has to attract students. So passing to the subject of the presentation, why do we want to use that byproduct in producing a very special type of concrete? One of the main claims that our industry has is to reduce the CO2 emissions. And one of the ways to do that is to substitute the cement or the cementitious material, use it in the production of concrete for certain byproducts that are very popular in the industry, but they are not so available anywhere. Okay, I mean fly ash, byproduct that Ramon used to work a lot with it, silica fume, ground granulated blood furnace slag, but they are not available, and they won't be available in the future as we want. So that's why we are considering this byproduct and to produce the cement, mainly the cement in this type of concrete. Why the cement? Because this type of concrete demands around 800 or 1,000 kilograms of cement per cubic meter. So that's a major benefit if we can diminish the amount of cement. So these type of concretes were developed between the 1980s and the 1990s because the appearance of the high-range water-reducing admixtures that allow us to produce concrete with very low water binder ratio. So the purpose was to see how far we can go in terms of strength, and at the same time, how far we can go in terms of durability. So these concretes are considered ultra-high performance concretes when they have a minimum strain of 120 megapascals. it can be produced easily, actually, with 200 megapascals, but it depends on the ratios. So the first development appears in France and in Denmark in the 1980s, 1990s. And to improve the brittleness of the material, the solution was to incorporate a significant amount of fibers. You can see in the pictures, and you can have an idea of how much fiber that concrete has. Okay, so it goes from 1% by volume to 3%. In our case, we use just 1%. And also, actually, these concretes are becoming very popular for architectural applications, as you see in the bottom pictures. So the fibers helps to give ductility to the concrete. Okay, so because concrete is a brittle material, it's not a ductile material, so without those amount of fibers, it reaches almost the ductility of steel. Okay, almost. Okay. So what do we do? What do we use? We use a silica fume, of course, a polycarboxylate high-range water-reducible mixture. Limestone powder that is produced by the grinding of a limestone aggregate in Monterrey, Mexico, and vitrified clay, limestone sand, and the steel fibers. Those that you see in the picture are the first generation of fibers used to produce this kind of concrete. Now, the company Bakerhurt, the name is Dramix, they have a new generation of fibers of this type. But now, also in the market, you can find some polyvinyl alcohol fibers that almost reach the performance of the steel fibers. Okay, so this is the knowledge about ultra-high performance concretes and the materials that are available to produce it are becoming very popular in these days. So those are the particle size distribution of the different granular materials that we use. And you can see the average particle size of the materials, the limestone sand, the limestone powder, and we prepare the vitrified clay in 4 different particle size distribution to substitute cement, silica fume, the limestone powder, and the sand, the limestone sand. So those are the 4 materials that we obtain by grinding and pulverization, and you can see the particle size distributions of the materials. As a first, one of the first steps that we make is to evaluate the compatibility between cement and the superplasticizers. The graphic on the left, that's the result for the cement pastes. And the graphic of the right is the pastes with cement and silica fume. So you can see that the bottom graphic is for the admixture that results more compatible with the mixture with cement and silica fume. So this, as you can see, the variations is very important in the development of these materials, to make this test to define which admixture is the one that gives the best performance with that specific cement or that specific binder. Okay. And also another important step in the process is to ensure the maximum packing density of the particulate materials, and for this purpose we use the Andreasen and Andersen model. So with this model we define the combination of cement plus silica fume plus limestone sand plus limestone powder, and that lead us to obtain the maximum packing density. Okay, that's another important step. So the concretes were produced with a water to cement ratio of 0.25, and we fix a cement content of 800 kilograms per cubic meter, and we establish a target spread of 325 plus minus 25 millimeters on the flow table that you see on the right, and is the flow table used to determine the flowability of mortars, standard mortars. And at the end, the optimal mixtures, we produce it with 30% of limestone sand substituted by vitrified clay sand, 30% of limestone powder substituted by vitrified clay powder, and 30% of Portland cement by vitrified clay fine one, and we substitute 100% of silica fume. You can see how was the flowability of the concrete that we produce. It's not really a concrete, it's basically a mortar because it has only sand. Okay. And these are the proportions that we use. So you can see in green the cement for the reference mixture. Okay, so it has around 700 kilograms of cement and 80 kilos of silica fume, and those were decreased in the what we call green concrete to 500 kilograms of cement, and also the silica fume was substituted 100% by vitrified clay. Okay, so these are the also we determine the times of setting. Okay, so it's important to determine this property when you substitute cement and a supplementary cementitious material, and it basically remains the same with this substitution of cement and silica fume by vitrified clay, and the air content of the mixtures was result between 1.5 and 3.2%. Okay, and this is the graphic of the loss of the extensibility that is important for practical and industrial applications. And what we can see in the top, the red graphic is the one for the green concrete. So we can see that the blue ones that were made with the cement, the referent ones, lost the extensibility in a shorter time. So the green concrete has give us more time to work the mixture, and that is because the vitrified clay doesn't have the same reactivity as cement, so it gives us more time to handle the concrete. But you can see only 80 minutes, so this is a good application for precast industry. Okay. So these are the compressive strength results. You can see the compressive strength development in the graphic that is in the top, okay? And we can see that the major compressive strength development is obtained between the first 7 days, okay? And in the bottom graphic, we can see that the presence of the vitrified clay gives higher strength since the age of 60 days, and that is attributed to the puzzolanic activity of the material. The modulus of elasticity in the case of the reference concrete decreases 3.46% in the concrete that has fibers, so the fibers lead to a decrease of 3.46%, and in the case of the green concrete to 11.34%. In the case of modulus of rupture, okay, we make some beams. That's the strength that we obtain for the beams without fibers. And these are the graphics that we obtain for the two concretes with fibers. So as you can see, those points that appear in the graphics, the A means that when the first crack appears in the test, and the other are the toughness indices that are established in the literature to determine the toughness of the material provided by the presence of fibers. Okay, so these are the limit of proportionality. So we can compare the blue with the green one, and that's the strength of the concrete at the moment of the first crack, and the red ones are the maximum residual strength, and the orange ones are the maximum toughness at the end of the test. And in the other graphic, we can see the accumulated toughness. So we can see that the improvement of the material attributed to the presence of fibers. Another important thing that we find, we measure the autogenous shrinkage of the concrete, and we see that the vitrified clay originates a reduction of the autogenous shrinkage of 400 microns per millimeter, that is 61%. And this is a very good performance, because this concrete, as a result of the high cement content, they normally present very high autogenous shrinkage, around 1,000 micrometers per millimeter. So it was a very good finding. And also we estimate the embodied CO2, and for the green concrete compared with the reference concrete without fibers, it reached to a reduction in embodied CO2 of 27.24%, and in the case of the green concrete with fibers, of 20.19% of the embodied CO2. So in conclusions, the result of this work evidenced the technical feasibility of a specific vitrified clay to be used in the production of ultra-high performance concrete, with the incorporation of 30% silica fume of cement, with the substitution of cement by 30%, 100% of silica fume, limestone sound powder 30%, and without detracting the properties in fresh stage and hardened stage, and also with an important reduction of the embodied CO2. Okay, although the results and uncertainty indicators reported in this work were obtained for experimental laboratory tests, these constitute an exhortation for the precast concrete industry segment, since it is a sector in which rigorous procedures are commonly implemented for quality assurance, through which it will be expected that the variation in the results in relation to those obtained in this work will be minimal or negligible.